with us the old processor fans with heat sinks. We will make use of two of these fans to fix on both sides of the Peltier module. In one of the fans, current consumption is listed at 0.33 amps and in the other fan, it's listed as 0.24 amps. Since the fan with 0.33 amps rotate faster, if we use this fan on the hot side, we will be able to dissipate maximum heat from the hot side of the module. More the amount of heat removed will give us a chance to get greater chillness. In order to connect the two heatsinks to the Peltier module, we need to drill holes on these two heatsinks. Let's mark this part and then drill the holes. Now we have drilled holes in both the heatsinks. Let's see if this fits on the Peltier module. Alright, that fits perfectly. The side where the text is present is the hot side and the plain side is the cold side. This is a chiller box. We are trying to convert this into a fridge. The plastic walls around the chiller box are usually stuffed with styrofoam. This prevents the outside heat from entering inside the box. If we are able to place the cold side of the heatsink inside the box, our fridge will be operational. To place the heatsink inside the chiller box, we need to cut a small portion from the outside of the chiller box. Let's fix a strip of heat-resistant Kapton tape to protect the wires. Let's measure the size of the aluminum frame. The length measures to 83.7 mm, the width measures to 68.6 mm. Let's mark the spot on the chiller box that needs to be cut. We'll use a cutting wheel to cut along the markings. Voila! The opening to place the aluminum plate is now ready. Let's file away the rough edges and smoothen the sides. Let's now insert the cooler module. There could be small gaps along the plate which can be stuffed with the thermal insulator. The gaps inside the box can also be fixed with thermal insulation tapes. We will be drilling a small hole to bring the fan wires outside. Let's now apply the thermal grease on the aluminum plate and place the Peltier module on top of that. This can give much better heat conductivity. We will place the Peltier module around the heat insulator and fix the heatsink using screws on top of it. We will now fit a fan on top of this. Fill the gaps using silicone glue. Let's now connect the Peltier module and the fans to the power supply unit and check. Let's start at 12 volts. I'm wondering why it's consuming less current than what I had anticipated. Alright, let's check the chillness. I can feel the chillness, but still as per the module's datasheet, at least 4 amps of current should have been consumed. Including the fan, it should have consumed around 4.5 amps. The meter showing consumption of 3.5 amps would mean that there could be something wrong somewhere. Maybe the heatsink could not dissipate the heat properly, but note that this heatsink was taken from an old CPU and is not dedicated to being used in our experiment. Still, we will continue to monitor the temperature drop inside the fridge and go on from there. We have a digital thermometer with a sensor extendable by a 1 meter wire. Let's drill a small hole on the chiller box to insert the sensor and seal it with glue. Let's test the cooling by placing a glass of water inside the box. It's been an hour. I still see the temperature at 19 degrees Celsius. The water seems to be cold, just enough maybe for a milk packet. But still, 19 degrees is too high. Let's see if this can drop further. It's been 2 hours now. There is no drastic change in temperature. It's at 18 degrees Celsius. It has not dropped much. We will have to figure out if there are any other options. Let's redo this and use another similar Peltier module and check if the temperature drops. But this time, I am going to use 2 small fans that were specifically designed for this module on the cooling side. Let's arrange the heatsink and the fan on the module's hot side. Since the maximum current output on my RPS is 5 amps, I will be using a dedicated power supply for this. You can also use the SMPS from your old computer. The dedicated power supply I am planning to use can source current up to 10 amps. One Peltier module will consume a maximum of 6 amps of current, but we will not be operating it at its peak. We will still be testing it by adjusting the voltages. That's why we would be needing an adjustable power supply. This is the wiring diagram of our fridge. If you see this, we are using two types of power supply. I have connected both the Peltier modules to my 10 amp power supply. The fans inside the heatsink would also need a separate power supply. I am going to use my regulated power supply to draw 12 volts for this. All the fans together consume around 780 milliamps at 12 volts. Additionally, the Peltier modules are consuming around 6.9 amps at 15 volts from my SMPS. Altogether, we can see that the total power consumption is around 112 watts. This seems to be an inefficient design. We now need to reduce the power consumption as much as we can. A typical fridge at your house is not kept on all the time. The compressor switches itself off when a particular temperature is reached, and when the temperature gradually increases, the compressor switches itself on again. This mechanism saves power. Let's adopt the same method in our design. We can design a program to switch off the Peltier module once a specific temperature is reached and switch it on again when the temperature rises. Let's now design the electronics to achieve this programmatically. Let's use the temperature sensor that we saw in the mailbag series for this purpose. This is a DS18B20 digital temperature sensor. This has an inbuilt analog to digital converter which can be programmed for 9 or 12 bits. This device also supports a one-wire protocol. Using the one-wire bus, we can exchange data using just a single data line. This doesn't need a dedicated power supply. Of course, we would still need a ground signal. We can just use a ground wire and a data wire to exchange data using this sensor. In order to harvest the power from the data line, the sensor contains a parasitic power supply. The microcontroller is a master. Once the master sends a request, the sensor responds with the temperature data. I have now interfaced the temperature sensor to the ESP8266. Additionally, I am going to use an OLED display to monitor the temperature locally. I need a 5V input for the microcontroller. I already have a 12V RPS output. I will be using a step-down converter to convert the 12V to 5V. In order to arrange all the electronics inside a compartment, I have designed and 3D printed an enclosure. Let's arrange the step-down converter, microcontroller, and the display inside the box. We will drill a small hole and place the temperature sensor inside. We will now interface the sensor with the ESP8266 and try to control it using MicroPython. Here is our MicroPython code. You can find a detailed explanation on this on my instructables page. The links are provided below. Let's try to run this code. This will poll the sensor data every second and display it on the OLED display. I have a relay module with two 12V relays. We have to connect a 12V supply input, 3.3V logic level input, and 2 pins from the ESP8266 to toggle the relay. We can combine the two Peltier module and connect it to one of the relay outputs and the 4 fans to the other relay. We will now solder the wires as per the wiring diagram and tape the module to the side of the fridge along with the 3D printed box. We will now connect both the relays to the GPIO pins 0 and 2. The relay inputs are active low inputs, which means only when we give 0, the relay will switch on. Alright, now that we changed quite a bit, let's place a milk packet inside and test the temperature drop. It's been an hour now. The temperature is 9.8 degrees Celsius. Let's check back after half an hour. Looks like it's reduced just to 9 degrees Celsius. It could drop to 8 degrees if we keep for some more time. There is little chance for it to drop below that though. To reduce the power consumption, I will be switching off the Peltier module and the fan when the internal temperature of the fridge drops to 9 degrees. When the temperature rises slowly up to 12 degrees, I will make sure the Peltier module and the fan switches on again. Since the on and off conditions alternate this way, we save power. Let's add this to the code as well and test it once. It's getting down to 9 degrees Celsius. It's now switched off. We see that once it reaches close to 12 degrees Celsius, it switches on again. Based on my testing, I see that approximately 25% of the power consumption can be reduced. I bought this milk packet in the morning and it's now evening. Usually milk packets can't survive that long. This packet has been in our fridge for so long. Let's boil it and see if it's still good. Let's keep our fingers crossed. Aha! What an escape! The milk is still good. At first I thought there is just enough space to keep a milk packet, but given the space inside, why not place some more items? Isn't that cool? Alright, we now have a working fridge.